Take 3. Oh, if you only knew. So this is the Pre-Calc Unit 8, Lesson 5 video on applications of exponential and logarithmic functions. And we're going to go through Warm-Up 5, which essentially covers the content from the previous lesson 4, which is solving logarithmic and exponential equations. And you really need that content before you go on and take this. You're going to want to make sure that you do the content from lesson 4 before you try lesson 5, because you're going to need to be able to solve an equation in order to answer the questions in unit 5. So if you haven't done lesson 4 yet, go back and do lesson 4. And then what I would like for you to do is come back and then you can do the warm-up here and move on to the lesson. Both the warm-up and the lesson notes should be posted to Google Classroom already. And what I would ask is that you not worry about if you can or can't print it, or if you don't have a hard copy of it, you can do this work on notebook paper. Every single thing in this lesson can be done on notebook paper, including the warm-up. So as I said, the warm-up for this lesson is a review of the equation solving from the previous lesson. So if you would go ahead and hit pause and copy some of these, copy these 4 problems down and work on solving them. And in a little bit, I will go on to just show you the answers, but I probably won't talk through much, if any, of the steps. Not my dog. But they're pretty cute, aren't they? I have the answer to number 3 in a different part of the page because it was too big. So anyway, I wanted to give you 1 and 2 first, and then I have to scroll a little bit to get to the answer for number 3. So here's the answer to number 3. And then here's the answer to number 4. For number 4, make sure that you see that the -4 is extraneous, because both in let me pull up a color. Both in the first logarithm, log of -4, you can't do, that's undefined. Also, -4 minus 5 is -9, so both of the logarithms in this equation would be undefined if you used -4 as a substitution for x. And so -4 is extraneous, but 9 works just fine for both. So we're going to be doing in this lesson applications, which essentially means that it's the answer to the question, when would I ever use this? And I've been saying all along, talking about the number e, and the natural logarithm is used a lot in financial situations, and the main financial use for the number E is when you do continuously compounded interest. So what I want to do is start with compound interest and then just get a basic idea of what interest is, and then move on to continuously compounded interest. Then we're going to look at some other situations with growth and decay, and talk about things like population growth or radioactive decay, and talk about how we use exponential functions with the letter E in order to do certain computations of that nature. Then we'll move on the last page, we'll talk about some applications of logarithms, like using logarithms to compute pH value of acids and bases, and using logarithms to compute the strengths of earthquakes. So let's start with the problems on interest. And I didn't say at the beginning, and you clearly figured it out when you were doing the warm-up, but you really need to have either a calculator or Desmos in order to do these computations. And I will make some screenshots for a couple of the problems so that you can see. They're kind of tricky to type in because they've got, as you can see, the formula up there in the top right corner is kind of icky. But what I'll do is I'll show you how you can type the whole thing in at once and click enter. And so make sure that you have Desmos within reach while you're working on these. So just in case you've not done much with finances, which I can imagine when I was your age, I think maybe my parents put my money in a savings account and I never really paid attention to it. So I get that. Until you actually are paying your own rent and utility bills and trying to work out how your salary covers all of that, it's kind of tricky to understand interest. But the basic idea of, and this is very, very basic, the basic idea of interest is that some people have money that they want to save, and so they put their money into a savings account. And then the bank has all this money from all these people, and the bank can make loans. Let's say that I have my money in a savings account, and the bank has 8 million customers, and then my friend Joe wants to go buy a car, and he needs a loan from the bank, and the bank uses the money that people have saved at the bank to spot Joe the loan for the car. Because most of the time, unless there's an extreme financial problem like the crisis that happened in the 1920s when they called it a run on the banks, most people leave their money in a savings account and don't put it in and take it out the next day. And so the banks have a certain amount of, and there's a federal organization that insures the money that's in the banks. And so when things are working financially normally, and I understand that as you're watching this video, if it's 2020, that may not be the case. And so that's my little caveat. But in normal times, what happens is then that when the person who took the loan from the bank, like my friend Joe that bought a car, he pays back the loan, but because the bank did him the business of lending him money for his car, he has to pay the bank back extra. It's kind of like purchasing a loan, right? He pays back the loan, but he also has to pay the bank for the convenience of getting the loan in the first place. And so now the bank has collected not only the money back that they loaned to him, but they've also collected fees on top of that. It's called interest. And so come back to me, I haven't touched my money in my savings account for a long time, and so while my money is sitting there and the bank has been using it, the bank says, well, we need to pay Miss Applebacher for the convenience of using her money to run our business, to make loans to Joe to buy his car. And so in the long run, Joe pays interest and I earn interest, and of course the interest paid on a loan is going to be a little bit bigger then, and that we're talking averages, right? So on average, a bank is going to take in more interest paid on loans than they will pay to savings accounts because they need to earn their money in between there somewhere. And so that's really where a bank is going to earn their money. So in these three examples, we're talking only about savings account interest, but the idea of loan interest works the same way. And so you've got this formula, and in fact, before I zoom in on the formula, if you are a highlighter kind of person, this would be a really good time to have your highlighters out. It's important to know what the letters stand for. And so your principal is the capital P, and your rate is the lowercase r, and your rate is going to be given to you as a percent, but you need to change your percents to decimals. Remember that you can't ever do computation with a percent. You always have to change it to a decimal by moving the decimal point over twice, and I will go through that when we do the examples. It should be obvious to you as we're working through them how that works. Now, the next one, N, is how many times a year, and that number is in two places in the formula. And then the variable T is how many years is the savings account, or in other situations, loan. And it's important that N talks about how many times a year and T talks about how many years. If you were talking about two different quantities, then you can't use N and T here. You actually have to convert them into the same quantity. So now I will zoom in on the formula. On a test, you would be given the formula. Although there are some teachers that would ask you to memorize this, I feel like if this is something you end up doing for a living, you'll learn the formulas that you need. And actually, this is not a realistic formula. This formula is kind of simplified so that you can process what you're doing with it. But the way basic compounded interest, and let me actually back up and let's talk about the word compounded. So if I put $1,000 into a savings account and left it there for 10 years, and the bank at the end of the 10 years, when I walk in the door and say, hey, I want to take my money with the interest, if the bank just said, okay, we give 5% interest, 1,000 times 5%, here's your $1,000 plus your interest, and they just did one computation at the end of the time when I'm taking my money out of the bank, that is called simple interest. It's computed one time and it's handed to me at the end of the duration of my use of the savings account or the loan. Nobody does simple interest. Compound interest, and that's the word right here that is important in this context. Compound interest is that I put my $1,000 in the bank, and the bank computes the interest, let's say annually. That means once a year. So I put my savings in the bank in April of 2020, and in April of 2021, they compute the interest. But most banks wouldn't then send me a check at my house. They would put the interest back into my savings account. So let's say that it's 5% interest, and 5% of 1,000 is $50. They take that $50 and they put it back into my savings account. So now I have $1,050. And then in April of 2022, now they're computing 5% of 1,050. And when they compute that, they put that back into my account. So if I don't touch my savings account and just leave all that money sit there, my interest earns interest, earns interest, earns interest. And if I come back 10 years later, not only did my original $1,000 earn interest 10 times, but it also had interest earned on the interest each year. So the first $50 earned interest 9 times, and then the second interest payment earned interest 8 more times, and that original $50 that wasn't even mine to begin with earns interest, and then earns interest, and then earns interest all those times over and over and over again. So you're basically earning interest on your interest, and that's the idea of compounding interest, is that you're earning interest on your interest. which is another reason why you really want to pay down your credit cards, or at least be on time with the minimum payments, because you're actually, they'll take the interest that you owe them and compute interest on that interest, and that's money that you owe the bank, not money that the bank is giving to you. So anyway, what we're going to do is we're going to play around with this formula a little bit, and I will walk you through how to type this into Desmos, and give you some hints about how to type it into your graphing calculator as well. So each of these questions is asking you to find the balance after the given time. So that's at the end of the 10 years, if I had started with $1,000, that question, what is the interest what is the balance on the account? What is the total amount of money that you have in the account at the end of the given time period? So here I have $1,000 I've put into a savings account that earns 2.3% interest, and it's compounded annually. And so if I were you, I would start by saying, okay, and you're not going to need to do this every time, but just to kind of help you start understanding where stuff goes in the equation, here, P is your principal, that's the original amount. So your P value, or your principal amount, is $1,000. And you also want to know your interest rate, R, but they're telling you R as a percent, and you want to make it a decimal. So we're going to move the decimal point over twice, so it's going to be 0.023. That's the same as 2.3%. That's your rate. And then it's N times per year, so N is, and if it's annually, that means once a year. And last but not least, the number of years here is 5 years. And so when I substitute into my formula, the capital A, is the amount left at the end of the time frame. And so here, the amount at the end of the time frame equals, and then P is 1,000 times parentheses. This number will always be 1, and we'll talk about that in a minute. And then the fraction there, that's kind of an ugly fraction, is going to be 0.023. There's your rate, divided by your N value, which is number of times per year, so that's 1. And then you've got an exponent that's a multiplication problem, and it's 1 times 5. I know, you're thinking to yourself, well, I don't need to write divide by 1, and I don't need to write multiply by 1. Let me make a recommendation that for now, even though you know you could do this without dividing by 1 or multiplying by 1, why don't you go ahead and type those in anyway, just to make sure that you have the process of typing these numbers into your calculator or Desmos with the fraction and with the big exponent with the multiplication in it, because sometimes it's not going to be 1, as you'll see in some of the other problems. So let's just practice with the ones there as if it were a different number than 1. So here I have a screenshot from Desmos, and when you're typing this in, when you start typing an open parenthesis in Desmos, it will give you that kind of grayed out closing parentheses, and you type what's inside, and then you either close the parentheses by typing another close parentheses, or you hit right arrow and it'll get you outside the parentheses. But you have to acknowledge that you're at the end of one set of parentheses. So I had said that I was going to put the 1 as the denominator there, but because I have not yet been able to figure out a way to make Desmos keep a multiplication problem in an exponent without actually putting parentheses around it, I have parentheses there. And if you know a way to do that without the parentheses around the 1 times 5 and have both the 1 and the 5 be still in the exponent, by all means, let me know. When you are typing all of this into a TI calculator, you do the same kind of process here, where you take your principal amount, the 1,000, and then type parentheses, and then literally type 1 plus. But then right there, you can hit alpha y equals enter to get your fraction. Type your numerator and denominator. Then you have to right arrow to type another parentheses. And then you do the little caret or the upside down V to make the exponent. I don't think that in the graphing calculator you need the parentheses around the exponent. I think the graphing calculator assumes that if you are still typing in the exponent that that's where you mean to be. Desmos tries to make that decision for you. Anyway, make sure that you understand how to type all this in and that you understand where the substitutions go. And when you see all these decimals here, remember that it's money, and in the United States, we talk about money to 2 decimal places. So the final amount in that savings account is $1,120.41. Now, I'm going to give you some time in a minute to work on B and C, but let me just point out that if it says quarterly, that means 4 times a year, so your N is going to equal 4. And then in letter C, if it says compounded daily, your N value is literally going to be 365. So take a minute and work on B and C. I don't have a fancy press pause logo right now, but copy down what you need from the problems. Press pause, please. And I will come back in a moment with these answers. Here are your answers for B and C. Take a quick look at the substitutions. Make sure you understand why everything is where it is. I said that I would come back to the 1 plus stuff and that number that's always 1. And I want you to think about, ignore the exponent for a second. And if you think about the idea of your principal being multiplied by itself, because you want your principal back. If I put $1,000 in the bank, when I go back in 5 years, I want to get that $1,000 back plus the interest that I'm earning. Now, if they compute the interest quarterly, they don't compute 5% each time quarterly. They compute a fourth of the 5%, but because you're getting interest dropped into your account at the end of the quarter, and at the end of the second quarter, at the end of the third quarter, at the end of the fourth quarter, then although they're breaking the interest into the 4 parts of the year, you're still earning that little bit of interest on the stuff that was the interest from the previous quarter. So there's your answers for A, B, and C. And the thing that I want you to think about is that having the interest compounded on itself ever is better than not having compound interest. But compounding the interest 4 times a year is better than just once a year. And because you're getting interest on interest more often. And then having the interest compounded daily 365 times a year is way better than having the interest compounded 4 times a year. Well, what if they did it twice a day, or 10 times a day, or 24 times a day, or 800 times a day? What about if they just compute the interest and compound it constantly? And so they call that continuously compounded interest. In fact, this equation is easier to work with than the not continuous interest, because the E takes the place of the 1 plus fraction. So you see you have the same idea of the rate times the time. The rate here is being multiplied by itself, the number of times that's in the exponent there. And so you have the E takes care of the idea that you're adding to the interest and computing the interest on the interest over and over and over again on an ongoing basis. So the variables mean the same thing. P is the principal, E is the number E, R is the rate, but you have to change it to a decimal, and T is the amount of time in years. So again, this is asking for your balance at the end of the time. It's a number of years for each scenario, assuming continuously compounded interest. And so, for example, here, your principal, let's do this. Your amount equals the principal times e to the RT power. And so your principal here is 1,000 times e, and then the rate is 0.023 for 5 years. To color code things for you there. And let me real quick, I can pull up a screenshot of how this looks in Desmos. Remember that you can just use the E key on your computer, or if you have a graphing calculator, you use the second LN button. So 1,000 times, I don't know if you actually even have to type that times sign. I do it just to be sure. You might not need it. In Desmos, I find that I have to put parentheses around the exponent multiplication problem. We talked about that a minute ago. So now you've got 1,000 times e to the 0.23 times 5 power. And in the graphing calculator, I don't think you need to put the parentheses, just 1,000 times and then second ln to get the e. And the cursor should already be in the exponent place. And your answer here then is 1,121.87 or 87 cents. Now, before we go on, what I want you to look at here is that problem 1A and problem 2A are dealing with the same amounts of money, $1,000, 2.3% left in the bank for 5 years. But in 1A, you're getting your interest compounded annually, and in 2A, you're getting your interest compounded continuously. You may be thinking, well, I get $1.40 something more. That's not a big deal. Well, maybe not a big deal. It's still more. And trust me, the banks don't always like to give you your pennies. But the other thing that I want you to think about is that as you get older and deal with more money for mortgages or rent or utilities or whatever, $1,000 doesn't last very long in this day and age. And so you're probably not putting $1,000 into your savings account. Hopefully you're putting more than that into your savings account. But you should have, they say, 6 months of living expenses or your salary saved up in case you lose your job or whatever. And so if you're looking at several $1,000s, every little bit helps. So you're going to earn more interest on continuously compounded interest than on straight compound interest computed a finite number of times. So what I would like for you to do is do numbers 2B and 2C. Pause the video. Again, I don't have a little pause button, but pause the video and I'll be back in a second to give you the answers. So here are your answers for 2B and 2C. Take a moment, check your substitutions, make sure that you know how to type all of this into the calculator. And I'm going to move on to number 3. So number 3 asks for different things, not the amount at the end of the savings period, the length of the loan or whatever, but it is asking you in one case for the principal, you find the principal, or in another case, what's the rate, or how many years would this take? Because you might want to compute, look, I know what the interest rate is, and I know how much money I need to have 5 years from now. So I need to know how much money I need to put in the first place with a certain interest rate in order to earn such and such amount of interest. So here, for example, you're going to solve for the principal. So you want to have $5,000. That's your A value. That's your amount at the end, amount after 4 years. The 4 years, that's your T value. That's how much time you're leaving the money in the savings account. And your rate here is going to, let me get a different color. Oh, look, that's a good color. So your rate here is the 3.5%, but remember that you have to move the decimal point over twice, and so your R value is going to be 0.035. Now it says compounded daily, and so that's not the continuous compounding formula. That is the formula at the top of the page. So here in that formula, A equals P times 1 plus R over N to the N times T formula. And I'm going to substitute the things that I know. So I'm going to say, look, A is 5,000. I'm solving for P, so I don't know P. 1 plus, and then the rate is 0.035. So 0.035 divided by, and then N is, sorry, I should have put that at the beginning. So daily means that N is 365. And so it's 0.035 divided by 365. And then the exponent is 365 times 4. Now, I think that it would be best to solve this equation without doing any computation until you get to your very last step. And so I want you to kind of think through this with me. You're solving for P, and this entire thing right here, the parentheses with the exponent, all of that is just one big number, right? You could type that whole thing into your calculator and get a number, a numerical answer. So this is P times a number is equal to another number. So it's just 5,000 divided by all that blue stuff with the parentheses and the exponent and the highlighting in blue. So really, P is going to equal 5,000 in the numerator over parentheses 1 plus fraction 0.035 over 365 to the 365 times 4 power. And that's actually what you're going to type into your calculator, is big ugly fraction with even a fraction in parentheses and exponents in it. And what do you know? I actually have a screenshot of that. So start by hitting the divide sign. That creates your fraction. Type your 5,000 in the numerator. go to the denominator, parentheses, 1 plus, and then make another fraction by hitting the divide sign. And then the 0.035 over 365. You have to right arrow to get out of the fraction. And then type your closing parentheses, and then do your exponent. I needed to type parentheses. If you can find a way to do it without it, let me know. 365 times 4. And you should get the answer that your original principal needs to be $4,346.82. I'm actually going to walk you through all of 3A, 3B, and 3C because they're just a little bit tricky. So take a minute and take a look at B. So in B, it feels like they've not given you enough information, but they actually have. So let's start with the fact that the rate is your unknown. So you are looking for the rate at the bottom of the problem. When we do all of our computations, your answer is going to say something like R equals, and then it's going to be a decimal number. Remember that we've been computing R as a decimal, but it's always given to us as a percent. You're going to do that same thing in reverse. This time your answer is going to be R, and it's going to be in a decimal, but you're going to change it back to being a percent. So the question is, what's the rate of interest? It's compounded monthly, and so that means that your N is equal to 12 times per year. The time, T, is 10 years, so T equals 10. So I have T, I have N, I have R, but I feel like I don't have, or I need to find R. I feel like I don't have an initial amount or a final amount. Let's just pause and listen to the clock. Well, because it keeps going, you know, it can't just be short. I only notice it when I'm making a video. I don't even realize I have a clock until I'm making a video and the clock goes off while I'm talking about compound interest, which is really way more important than having a clock. Anyway, sorry about the clock. You feel like you don't have an initial amount or final amount, but it doesn't matter because we're talking about rates. And so whether your initial amount is 1, if it triples, it's 3, right? Well, who's going to invest $1? But let's say you start with $1, it triples, it's becoming $3. Doesn't matter if you're talking about $1 or $1 million, but pick an amount that doesn't have a lot of digits because then the numbers are going to be easier to work with. So just pick an initial amount and then triple it, and there's your principal and your amount at the end, or your P and your A. So I'm just going to randomly say that my P here is $1 and that my amount at the end is $3 because that's tripled. If you really, really want to be sure, run this problem with different numbers, but don't make them big because you'll be annoyed with yourself for picking big numbers is all. Make them big if you want to, but I think you're going to not want to. Make your principal $2 and your A at the end is $6, or make your P equal to $9 and your A equal to $27. You should still get the same answer that I'm getting. So, moving on then. This is the formula with the 1 plus fraction. So A is $3 equals P, $1 times 1 plus, and then that fraction is the rate that we don't know divided by 12, meaning 12 times a year. And then that same number, always, 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 always this and this are going to be the same number times the 10 years. Well, now look what I did for myself here. The first thing that I want to do is to get rid of that 1. And so I'm going to divide. Oh, I don't really need to do that because it's just 3. So 3 equals 1 plus r over 12 to the 12 times 10 power. Now watch this. ln of 3. Because I have to extract that r from those parentheses, and with the exponent, I can't just I just can't subtract something to get it by itself. So I need to deal with the exponent. Anytime an exponent is a problem, because you can't get at what it's a power of, then you can take the ln of both sides of the equation, and then you can make that exponent into a coefficient instead of an exponent. So what I'm doing here then is saying ln of all of this, I need to get that r by itself. And so now that 12 times 10, I'm just going to do that, 120. Yes, 12 times 10 is 120. And it became, it was an exponent, so now it has become a coefficient, times ln of everything that's in the parentheses. Now here's the sleight of hand. Sometimes mathematics is about the sleight of hand. I want the ln on the right to be by itself, so I want to get rid of that 120. But now the ln on the left isn't by itself. But think about this. First of all, make sure you understand all my steps there. If you understood the previous lesson, you should be okay with this problem so far. And I want you to look at this ln of 3 over 120. When you divide a number or something by a number, isn't it the same as multiplying by 1 over? So 1 over 120 times ln of 3 is the same. And then this 1 over 120 can become an exponent on the 3. It was a coefficient, but let's say that I asked you to condense that. You would then make that an exponent on the 3. So this is now ln of 3 exponent 1 over 120 equals ln of all the stuff inside the parentheses. Well, now I have ln of something equals ln of something. I can just drop the logarithms. So it's still ugly. This problem is just ugly. It's just going to be ugly. But now I have here 3 to the power 1 over 120 equals 1 plus r over 12. Now, I'm going to do all my number manipulation first, and then I'll type everything into the Desmos or the graphing calculator. So I'm going to subtract 1 from both sides. So 3 with this big ugly exponent here, minus 1 equals r over 12. And then I'm going to multiply, because I want the r by itself, so I want to multiply both sides of the equation by 12 so that those 12s cancel. So now I have r is equal to 12 times 3 with a big ugly exponent minus 1 in parentheses. Stop for a second and just soak that all in. And then I'm not going to walk you through this one. Go ahead and type that into Desmos. And it should give you something like r equals 0.11 and some stuff. But what you want to do is you want to say the rate is 11%. Because you want to give rates as percentages. I'm just going to zoom out on that for a second. Go ahead and pause that before we go on to letter C and make sure that you understand how I solved that equation. Now, Letter C is asking you to solve for the t value. So for how long, that means that you're solving for t. Initial investment means that P is 3,000. The interest is compounded continuously, which means that you're going to use the formula A equals P times T to the RT power, the one with the E in it. And it tells you that the rate is 2.5, so you're going to write the rate as 0.025. And that you eventually, there's your A value. So A equals $10,000. Hint. You want to start with $3,000 and you want to earn another $7,000 in interest, which is more than that's more than twice your initial investment. You're going to need either a really high interest rate, way higher than 2.5%, or you're just going to need to put it in there and never touch it. So let's say, for example, you're in your 20s or you're 18 and you're starting your first job and you're really good financially. You've got a good savings brain, which a lot of people don't have. So I would say that if you get it in your head now that you want to start saving and you put $3,000 from your first year of employment into a retirement account that might have a low interest, but doesn't matter because you're not going to even think about retiring until you're 60. So from your 20s to your 60s could be 40-something years. In that case, you'll have quite a bit more than what you started with, okay? And by the way, you want more than $10,000 to retire on. That's just yeah. So here, this is the formula with the E in it. We said that A is 10,000, that P is 3,000, and then E to the R, which is 0.025 times T, which is what we're solving for. Make sure that you understand my substitutions. Now I want to get the E with the exponent by itself, because then I can take the ln of both sides. And I'm going to need to take the ln of both sides because I have a variable in the exponent. So to get E by itself, I divide both sides by 3,000. And 10,000 divided by 3,000 is 10/3. Yes, does that kind of intuitively make sense to you? Now I'm going to take the ln of both sides. And remember that when you have that exponent there, let me keep what's on this side, that becomes then a coefficient, 0.025t times ln of E. But remember that the ln of E is equal to 1. And so really, this whole thing boils down to ln of 10 over 3 equals 0.025t. And so t equals big fraction ln of 10 over 3 divided by 0.025. Take a quick minute, look at all the steps there. Make sure that you understand each step. Plug all that into Desmos or a graphing calculator. And you should get, oops, why did I change from the pencil? Here we go. you should get t is equal to 48.16. So in order to go from $3,000 to $10,000, hang on a second. Years. Labels, please. In order to go from an initial investment of $3,000 to having $10,000 in an account that accrues interest continuously at 2.5%, you're going to need to not touch it for 48.16 years. Now, if you are watching this video in 2020, you know that we're in the middle of the coronavirus pandemic, and I definitely don't want to talk about that a lot. So if you're triggered by that, don't worry, I'm not going to get into it in depth. But for those of you who find the statistical analysis here interesting, the ideas of growth and decay, pay attention to the words that they're using in the news and the flattening the curve, and think about the bell curve that you learned about in Algebra 2 and statistics, and the numbers that they're talking about are all exponential, and the idea of the growth or decay of the numbers in the numbers of people infected by the virus are following an exponential model that is very close to the growth and decay models that we're going to be looking at here. If you're watching this video in a year that's beyond 2020, you might want to look back at some of the statistics that were collected starting in, let's say, January of 2020 and going forward in different countries or worldwide. I think that it'll be interesting to look back on later. That's all I'm going to say about the virus, though. I think that the most obvious application of a growth pattern is in population. And so populations tend to grow in a predictable manner unless something good or something bad happens. So, for example, let's say that you have a city that naturally sits on a waterway. I grew up in a city that was near one of the Great Lakes, Lake Erie. I grew up in Buffalo, or just outside of Buffalo, New York. A city like Buffalo or Chicago or Detroit, Michigan, or even Washington, D.C., which probably was chosen partly because of the Potomac River, because there's shipping value and people like living near water and people like living near the coasts. So if you have a city with a normal growth rate, it should follow an exponential growth rate, more or less. Obviously, it won't be exact numbers, but it should be a close approximation to an exponential model of a growth rate. Now, when I say unless something good or bad happens, let's say that you're from Skagway, Alaska. In Skagway, Alaska, one day the population was like just a couple of people. And then one of those couple of people discovered gold, and word got out, and the population of that city skyrocketed literally within a couple of months. And if that kind of story jazzes you, look up the history of Skagway, Alaska. It's fascinating how people descended on that. And it's kind of a landlocked city in Alaska. There's water on one side and there's ice fields on the other side, and people were crawling up over the mountains into the ice fields to try to get to where the gold was. But thousands of people appeared in Skagway, Alaska overnight, and there really wasn't space for them. It was crazy insane how fast that population grew. So that's not a normal growth curve. Or, and again, something that might cause a downturn in a population that is not normal would be, let's say, if a city grows up around one particular industry, let's say that there's a headquarters of, let's say, I don't know. Xerox is a company that had a headquarters in Rochester, New York. If Xerox closed one day, just shuttered and laid off thousands and thousands of employees that live in Rochester, and let's say that there weren't any other businesses. Rochester, New York actually does have a lot of other good businesses, but let's say that Xerox closed one day, and if Xerox was the only business that really anchored everything else in Rochester, then other businesses would start closing, and suddenly people would be moving away from Rochester. And it might happen all of a sudden. Like Rochester closed, or Xerox closes one day, and then by a year from then, Rochester's lost half its population because people need to move somewhere else to earn money. That would be something that I would say is outside the norm. But if you have a normal city, whether it's a small one or a big one, it would tend to follow a exponential growth curve that is based on this idea, this equation here. And what the amounts are, and I've got kind of an explanation up there. So I'm going to start inside the equation and then work to the left. I'm going to start on the right side of the equation, and then I'll address the left side of the equation last. So y sub 0 is the original amount of people that you're looking at. Now, obviously, the original amount of people in any place was 0 before anybody moved there, right? But let's say that we're talking about the growth of Washington, D.C. from the year 2006. 2006 would be year 0. And so the amount of people living in Washington, D.C. in the year 2006 would be what we're calling the original amount. Not the original amount back at the beginning of the world, but the original amount based on the time frame that we're talking about. So let's say that y sub 0 is the original amount. Notice that we're still talking about an equation that has an e in it. That's because the population would be considered to be growing continuously. There's going to be a rate of growth that's a positive number. We're going to call it K. And it's going to be different based on what we're talking about the population of. Because this formula doesn't only work for a population of people that live in a place, but it might also be applicable to, let's say, amoebas in a petri dish, or, which I'm not a science person, so I don't know anything about amoebas in a petri dish, but let's just pretend like I know something about what I'm talking about. The population growth concept is more of an exponential growth process. And so technically, your continuously compounded interest is this same exact equation, the initial amount times e to a rate times t. It's the same exact equation. It's just that with the finances, I gave you specific things to plug into different parts of the equation, but it's the same thing here. Y sub 0 is the original amount. E to the rate, which in this case is going to be K, and the, hang on a second, changing colors, and the time, and let's say that time is going to be in years. I didn't say that here, but time t should be in years based on this equation. And then I said that we're going to work our way to the left. So after a certain number of years, then all of the stuff on the right equals that number on the left. And the number on the left, the reason why we keep it on the left is because it's a function. And so y is a function of y sub 0 times e to the kt power. What the heck is she talking about? Okay, well, let's talk through a problem. And again, I'm going to give you these formulas so that when you take a test on this, you've got the formulas in front of you. I am not asking you to memorize the formula here, but understand how to substitute numbers into it. So let's say that I give you this formula that represents the population of Washington, D.C., Y years after 2006. And so the way that I wrote this formula, this 5.8 And I'm giving you the formula here, but that 5.8 is the initial amount. Now, you might be wondering, in 2006, did 5.8 people live in Washington, D.C.? No, because we're talking about hundreds of thousands. So the population of Washington, D.C. was 5,800,000 or 580,000 people in 2006. It was growing at a rate of 0.017 or 1.7%. And we want to substitute for t. And so in problem A here, I'm saying after 10 years, well, that 10 years is going to be your t value. So literally just start with the equation that I've given you. So y equals 5.8 times e to the 0.017 times 10. You can literally type this whole thing into your calculator to compute y. So go ahead and do that. Enter all of that in your calculator. And your calculator should be giving you a number like 6.87. But remember, your answer isn't 6.87 people lived in Washington, D.C. in 2016. Your answer is 687,000 people. So I do need you to do that conversion. So 687,000 people. Now, in letter B, it's asking how many years will it take for the population to double? Well, if the population started at 5,800,000, double is times 2. Do it. Don't wait for me. And you get 11.6. You waited for me, didn't you? So that is going to be my y equals. That's going to be my y value, and where this is my y sub 0, you know how there's the two y's in the equation? This is going to be where the 11.6 goes. So when I substitute into this equation, it's going to be 11.6 equals 5.8 times e to the, and then back to your little 0.017 times, and this time we're solving it after how many years? That's t, that's what we're solving for. So t is what we don't know. Now you really want to get the e with the exponent by itself. And so I'm going to divide both sides here by that 5.8. But we already multiplied 5.8 times 2 to get 11.6. So that whole thing ends up actually kind of looking a lot nicer. 11.6 divided by 5.8 is 2. E to the, well, it's still an ugly exponent, but e to that power. And now you want to solve for the t. Remember that when you have the variable that you're solving for is part of the exponent, then you want to take the ln of both sides. And so I'm going to have ln of 2 is equal to the ln of e to the 0.017 times t power. And I ran out of space there. So I'm going to bring that over here. Remember that this whole thing, that 0.017 times t becomes the coefficient, and ln of e is just 1. So now you have ln of 2 is equal to 0.017 times t. And it's technically times t times ln of e, but you don't need the ln of e because that's what equals 1. And so to solve this, then t is equal to ln of 2 divided by 0.017. And go ahead and type that into your calculator or your Desmos, and you should get t is equal to 40.77 years. So go ahead, I'm going to actually have you pause the video here, and I want you to see what you can do to kind of noodle your way through this example number 5. I would recommend that you pause the video, try to work it out on your own. I'll wait a minute so that you have time to pause it. And then I will actually talk through the problem, but I'll do so kind of quickly. I won't slow down. But check and see if you can get this worked out before I actually do it. Okay, so the growth rate here is 1.2%. That means that R is equal to 0.012. And the population year 2000, you don't need the number 2000. What you're saying here is that the initial population, this 12 million, y sub 0 is your 12 million. Treat million like a label. Don't write out 12 and then 6 zeros, because then that'll make you batty, because the problem will get really huge really fast. But treat 12 million as a label, and then any number that you get that has millions in it has that million as a label, which we'll get to in a minute with the 17 million. And so you're going to look for y, which is how many fish are there in the year 2000, or in how many years since 2000, sorry. And so you're actually computing that value t if your final population is this 17 million. So that's your y not sub 0. So y equals 17, y sub 0 equals 12, and your rate is 1.2% per year. And so this is, again, that y sub 0 formula up above. So it's going to be the 17 equals the 12 times e to the kt, and k we said is 0.012 times t, which is what we're solving for. Again, you want to get the e by itself, so divide both sides by 12. And so now you have 17/12 equals e to the 0.012 t. Leave 17/12 together, because now you're going to take the ln of both sides, ln of 17/12, and you're not going to change that to a subtraction, a logarithmic subtraction or anything. Just your goal is just to get that exponent with the t in it, not as an exponent. So over here now, you've got the ln of 17/12 is equal to, and then it's just that exponent, 0.012 times t. And so I'm going to totally run out of space. T equals, and then it's that ln of the ugly fraction, 17/12, all over 0.012. And then you end up with t is equal to 29.03, and we're talking about years. So the concept of decay is exactly the same as the concept of growth, except that the rate is negative. So your percentage, or your decimal number that is the k, is going to be a negative number. And remember that when you have an exponent that's a negative number, your answer is going to be a fraction or be smaller than the base that you started with. And so each time you use a negative exponent here, it decays the original amount. This, I'm assuming, is a formula that you've used, or something similar to this would be a formula that you've used in science class to talk about half-lives. And so the idea of a half-life here is that for an element that has a fast half-life, it's not very stable, and not very stable elements are the ones that aren't safe. That's my understanding. Mr. Hubbard may have something to say about my understanding, but that's what I think I understand. I'm no scientist. Don't tell Mr. Hubbard I said that. Let's just move on. So the problem here that you're given, and again, let me interrupt myself. The initial amount is your y sub 0. That's your initial amount. And your k is the rate, t is how many years, and y over here on the left is how much you have after that many years has passed. So let's say that we're looking at an 80 gram sample of this chemical, plutonium, and that's the initial amount. And we don't know how many years, so we're solving, or we're going to be substituting for t, and the function that you're going to use, the equation has been given to you. You don't even have to build it yourself. And so here, how many grams are going to be left after 6 years? So we'll start with this equation. We've already substituted for the 80. They're telling us the rate is a negative 0.02 times t, which is 2%, right? But they've given you the decimal version of 2%. We want to change the t to 6 because it says after 6 years, so 80 times e to the negative 0.02 times 6. And everything on the right there is a number now, so you can just plug that whole thing into your calculator, and y equals 70.95 grams. And so after 6 years, if you started with 80, if the half-life, if the decay rate of plutonium is 2% or negative 0.02, then you'll have 70.95-ish grams of the substance left after 6 years. So what I want you to do is try B and C on your own, and I will come back in a minute and give you the answers. So here you have the answers. Let me know if you have trouble with any of this, and we will see if we can answer your questions. And moving on, the last few problems will deal with the applications of logarithms. So we'll start talking about the use of logarithms, or the application of logarithms with the Richter scale. Kind of like with everything else that we're talking about, some of these formulas are overly simplified. So if you talk to somebody who's an expert in the Richter scale, they'd be like, well, what kind of formula is that? But this is something that I pulled out of a textbook, and it kind of, like I said, it oversimplifies, but it simplifies the idea that the way they measure earthquakes is logarithmic, which means that an earthquake that's a 2 on the Richter scale and an earthquake that's a 4 on the Richter scale, it's not that it's twice as strong, but that it's a logarithmic growth. So we're going to use this formula here, and the value of this lowercase a is the amplitude of the vertical amplitude. Remember, the amplitude is how high. Remember that the amplitude of the graph and the sine and cosine curves. If you have ever been through an earthquake, I have not, but if you've ever been through an earthquake, what they say is that it looks like the ground is rolling like waves. Like I had a friend who was in Seattle when they had an earthquake in Seattle once, and she was with her son in the parking lot, and she said the whole parking lot looked like it had turned into the ocean, and the parking lot was just rolling. So if you talk about the amplitude there is the vertical ground motion. T is the period. There's another one. So the period of the seismic wave, you're talking about a periodic function, and the period is the length of time that it takes to complete one cycle in seconds, and it's given in seconds. And then B, this is the part where I'm kind of skeptical. B is a factor that accounts for the weakening of the seismic waves. So assuming that a big strong wave happens, and then a lesser wave happens, and then a lesser wave happens, and then a lesser wave happens. So instead of, I'm picturing, based on this description, that an earthquake would be like this. So that whereas in the sine and cosine curves, the height of the curve is the same every time, what this B factor is saying is that it's accounting for the fact that the waves are weakening each time. Again, I don't know how accurate that is. I'm pulling this out of a textbook, and I have no idea how much research they did into this formula. But you can start with the fact that the Richter scale that measures earthquakes is a logarithmic function. It's just probably a little bit too complicated for us to do as new logarithm users. Like new users of a video game. So the intensity of this earthquake, I'm looking at example 7 now. The intensity of this earthquake has an amplitude of 250 microns and has a period of 2.1 seconds, and this magical B number is 5.4. And so we're going to take all those numbers and we're going to substitute them into that formula. So R equals, and then it's going to be log. And notice that your log doesn't have a base, which means that it assumes the common logarithm, or log base 10. So log of, and then 250 over 2.1, and then plus your magical B number plus 5.4. I probably shouldn't say it like that, because then somebody will throw me on the rug for mocking Richter scales. You can literally plug all of that into your calculator or Desmos, which you should do before I get to giving you the answer. And that would be a 7.48 on the Richter scale. So you were probably alive, but I don't know if you would remember, because it happened a number of years ago. But there was an earthquake in D.C. It was actually during, I want to say it was during the summer, because I was visiting some friends in New York that were in New York City. Just outside of New York City, and we were at a restaurant, and my friend turns to me out of nowhere and she says, "Stop pushing the table." She was really mad at me because I was wiggling the table. And I said, I don't wiggle the table. And I looked up and I saw a mirror on the other side of the restaurant that was wobbling. And I was like, that's really weird that she thought I was wiggling the table and I wasn't even touching the table. And there was a mirror at the same time on the other side of the restaurant that was wiggling. And that was that. And when we got home that evening, the news said that DC had this earthquake. And so you probably remember that then the Washington Monument was in repair it took several years for them to actually get the Washington Monument repaired. And the National Cathedral had some damage done to it, and some other buildings in downtown had damage done to it. But what was interesting to me was that I was in New York City and could feel the earthquake in DC. So the earthquakes are massive, and it kind of reminds us of what a little finite space we take up on the face of the earth. And before I get way too philosophical, because I don't like being philosophical, let's then talk about the District of Columbia. It's not concerned about earthquakes with an intensity less than 3.5 on the Richter scale. And so if such and such kind of an earthquake happens in DC, amplitude of 125, a period of 0.33 seconds, and the B number is 1.2, they basically want you to find the intensity of this earthquake and then decide if the earthquake is something that should start to concern seismologists in the DC area. So we're going to go back to the same formula. R equals the log of, and then it's going to be that 125 microns divided by the 0.33 seconds, which is the period, plus the B number, which is 1.2. Go ahead and type all that into your calculator. And you should get that R is equal to 3.78. And this number is greater than 3.5, so should they be concerned? So, yes, be concerned. Now, in this next problem, you are determining the amplitude. So, A here is what you're solving for, where it says the intensity is 6.1. Oh boy, hang on a second, sorry, clicking all kinds of bad things here. The intensity is 6.1. That means that on the Richter scale, it was a 6.1 earthquake. That gives you an indication of how long I've been working on this video. The period is 3.5 seconds, and your B number is 3.7. So your formula, remember, log of A over T plus B. So I'm going to substitute in 6.1 equals log of, now I've got A over, and then the 3.5 seconds, and then all of that plus 3.7. So make sure that you understand how I substituted there. And what I want is to get the actual log by itself. And so I'm going to subtract 3.7 from both sides. And then, of course, I didn't give myself enough space. So over here, then, 6.1 minus 3.7 is 2.4. And so that whole thing becomes 2.4 equals log of A over 3.5. Now, don't get thrown off here. I'm going to change colors for a second. If you need to, rewrite this with a base and with the logarithm over here on the left, because now you can just do a curly Q. 10 to the 2.4 power equals a over 3.5, and that's fairly easy to solve. 10 to the 2.4 power equals a over 3.5. I'm going to multiply both sides of the equation by 3.5. So a here is equal to 3.5 times 10 to the 2.4 power. And that you can just type right into your calculator or Desmos, and you should get 879.16 microns. And there's another thing, don't tell either of the Hubbards that I don't know what a micron is. What is a micron? So there's some problems using logarithms to talk about earthquakes. Last but not least, what I want to do is look at the chemical formulas around acidity and alkalinity, or acids and bases here. And it's just negative log of whatever the hydrogen ion concentration is, moles per liter. I loved science class in high school, and studying about moles was one of my favorite. This is why I knew I needed to be a math teacher. Learning about moles was one of my absolute favorite things, because the mole is always exactly the same number of molecules. That's what defines a mole. And I just loved the concept that you can have a finite understanding of exactly how many somethings there are in an amount, just because you know how much each of the little somethings weigh. It just was so mathematical to me that I said, oh, I have to major in math because moles are so mathematical. So anyway, so the number 10 here, asking you to test some apple juice. You find that the ion concentration is 0.0003. And so the pH formula then, negative log of that number. And again, type that in your calculator or Desmos, negative log, and it's common log, 0.003. 0003, sorry, there's 3 zeros. And you find that the pH is 3.52, and anything less than 7 is acidic. And it probably does not surprise you that apple juice is acidic. So is orange juice, by the way.